Hello everybody, my name is Anna-Lena Bours and I'm working as a research assistant at the Ruhr-Universität Bochum. I would like to welcome you to my presentation about the structural member stability behavior of steel channels. Girders of facade constructions of steel halls, platforms, gangways and stair stringers are examples of structural engineering in which steel channels are used. Mostly these monosymmetric C-profiles are loaded eccentrically to the shear center and the steel channels are subjected to scheduled torsion. Nowadays, the stability verifications for steel channels are usually based on second-order internal forces, although there are no generally accepted equivalent geometric imperfections and there isn't a generally accepted simplified method for steel channels and combined loading. Thus, the aim of the study is to supply a scientific background for steel channels and combined loading and to develop an analytical method. We made numerical simulations for the analysis of the structural behavior of these members subjected to scheduled torsion, extended existing verification methods, and reviewed their accuracy and consistency. The basis of our investigation is an experimental study performed within the German National Research Project P554. 8 simply supported steel channels with UPE 200 sections were subjected to a concentrated transverse force at its midspan and a concentrated axial force at its support, as you can see on this photo on the left side. The members had a length of 4 meters and 6 meters, and the transverse load was applied with a horizontal and vertical eccentricity to the center of gravity. In horizontal direction, the load application was varied between the middle of the web, marked as situation A, and the middle of the upper flange, marked as loading situation B. On the top right side, you can see some of the geometric values as well as the load application type of each test specimen and the load ratio of transverse to axial force. Bottom right shows the measured geometric imperfections as an example for test specimen 4. For the recalculation of these tests, we made geometric and material nonlinear analysis with imperfections. We modeled the steel channels with 4 node shell elements and idealized the cross-section by 16 elements in both flanges and the web. The additional stiffness of the fillets was considered by additional beam elements between the flanges and the web. And for the numerical simulations, we also implemented the measured cross-sectional values as well as the pre-deformations and pre-rotations. Due to the fact that there are no available measurements of residual stresses in channel sections, we considered the residual stresses which were theoretically obtained within the framework of the research project. The resulting stresses are shown here in the middle of the slide. Furthermore, we implemented the measured material properties into the quadlinear material model with strain hardening, shown on the right side of the slide. Corresponding to the previously mentioned aspect that no results of residual stress measurements on U-profiles are available in literature, I would like to briefly present some results of such residual stress measurements that I carried out in the last few months as part of an ongoing research project. Within the framework of this research project, Fabian Jörg from the University of Stuttgart and I are investigating the influence of different support conditions and structural systems on the stability behavior of steel structures. The residual stresses were measured in 3 UPE 200 sections by a sectioning method, and the cross-section was cut into individual lamella using the water jet cutting machine. During this process, the restraints introduced by the manufacturing process are released, and we measured the released strains with strain gauges at the inner and outer side of each plate. At the slide you can see the received residual stress curves and some extreme values. If we compare these results with the residual stresses which we applied for the numerical simulations, we can see that there are some similarities. For example, the tensile stresses at the right tip of the flanges are of same magnitude, and also the maximum compressive stresses at the left side of the flanges. For the web, the results are slightly different because the maximum tensile and compressive stresses are smaller, but overall the distributions are comparable. Now we go back to the numerical recalculations of the tests. As I mentioned before, we used theoretically obtained residual stresses for this, because at that time we had not yet made the measurements. The two diagrams compare the load rotation behavior of the tests with the numerical results. The dashed lines show the experimentally determined behavior, and the continuous lines the numerically determined behavior. The curves are shown separately depending on the loading situation. The left diagram includes the results of the steel channels with web loading, and the right diagram includes the results for flange loading. In some cases, the stiffness of the numerical model is a little bit higher compared to the behavior in the tests, but the deviation is within an acceptable range. The maximum deviation resulted for test member 3, and on average the deviations were around 5%. Then we analyzed the structural behavior of the members in detail. For this purpose, we examined the load rotation curve at mid-span, the development of internal forces, and the remaining elastic cross-sections for the increase of the loads. The left diagram in figure B shows the internal forces at mid-span, and the right diagram shows the internal forces at support. Here, the figures present the results of test member number 4. The static system is shown below left, and the simply supported member had a length of 3,810 millimeters with overhangs at both ends. It was subjected to an axial compressive force at the end of the member and a transverse load at midspan with vertical and horizontal eccentricities. The ultimate transverse load was 24.2 kN with the corresponding axial force of 227.9 kN. In order to describe the structural behavior of the member during the load increase, 5 deformation states were selected from state A to E. Point A represents the first deformation state. The left tip of the upper flange receives the highest compression stresses due to the superposition of the residual stresses and the internal forces N, My, and M omega, and consequently this part began to plasticize. In conjunction with the load increase, the rotation of the member and also the internal forces increased. And with an increasing rotation of the channel, the bending moment mz increased. Due to the superposition of mz and m omega, the plasticized part of the upper left flange expanded, and in state B, the maximum load was reached. So far, only this part of the cross-section is plasticized, and the cross-sectional utilization at midspan is about 89%. These two aspects indicate that the significant failure mode was stability failure. After the detailed analysis of the structural behavior, we now move on to 3 existing verification methods that we have extended and applied to the 8 steel channel members of the tests. First, we adapted the simplified method of Annex C of the pre-standard to cross-sections which are symmetric about the y-y axis like steel channels. The related equations are given in the left column of this table. Second, we exceeded the verification method according to Snyder, which is applicable for members which are symmetric about the y-y axis, but it is only derived for transverse loading without compressive forces and only for load application at the middle of the web. You can see the equations in the middle column. We have added a term for an additional normal force. Thirdly, we used the equivalent geometric imperfection method. The internal forces have to be calculated according to second-order theory, considering the effects of equivalent geometric imperfections. However, as I already mentioned in the introduction, there are no generally accepted equivalent geometric imperfections for channel sections in literature. Hence, we applied the Bours imperfections, which were derived for I sections. You can see them in the right column of this table. For a first assessment of the accuracy of these adopted methods, we compared the ultimate loads with the experimental results. We divided them depending on the type of loading. The members with load application at mid-flange are marked orange, and those with load application at mid-web are marked blue. The left diagram shows that the adapted simplified method of Annex C leads to over-conservative results compared to the experimental results. On average, the determined load capacities deviate by about 48% from the test results. Within a further development of the method, the specifications of cross-sections, which are symmetric about the y-y axis, have to be considered in order to increase the accuracy and efficiency. The middle diagram shows that the design method, according to Snyder, also leads to conservative results. Only for one steel channel subjected to flange loading, the determined ultimate load is about 3 kN larger than the test result. This method was only derived for channel sections subjected to web loading. Nevertheless, the deviations between the determined loads and the test results are within an acceptable range. The mean value of deviation is about 15%. The right diagram compares the equivalent geometric imperfection method with the test results. This method also leads to over-conservative design results for all cases. Here, the mean value of deviation is about 41%. This brings me to the conclusion. The first aspect I would like to mention is that the structural member stability behavior of steel channels is severally affected by the torsional internal forces. Since the loads are usually applied with an eccentricity to the shear center, the cross-section is stressed with high torsional loads. The load is predominantly transferred through warping and bending about the weak axis. The residual stress measurements on UPE profiles, which were only recently carried out as part of a research project, are comparable to those determined theoretically. The simplified method, according to Annex C of the pre-standard, can be extended to cross-sections which are symmetric about the y-y axis. However, it is necessary to further develop the method as the results are over-conservative. The verification method of Snyder can be extended to steel channels subjected to flange loading and to consider normal forces. Finally, I would like to give a brief outlook on my current research that is related to this topic. In the first part of my presentation, I already talked about the residual stress measurements that we have carried out as part of a research project that we are working on together with the University of Stuttgart. In order to investigate the influence of structural systems on the stability behavior, as well as the interaction of stability and plasticity, we are testing two-span members subjected to a transverse force at mid-span and an axial force at the support. A series of 20 large-scale tests is performed, 10 tests with a doubly symmetric cross-section, HGB 200, and 10 tests with a monosymmetric cross-section, UPE 200. Additionally, we investigate different load application points, which you can see here on the top left of the slide. The picture to the right shows the developed test setup. And there are also some impressions of the first tests. On the bottom left, you can see a video while the member is loaded, and on the bottom right, a picture of the test specimen at the time of failure. But as I said, it is an ongoing research and we will present the results next time. And now I would like to thank you all for your attention.